Let's see. Goal for today is to finish the classification.pdf notes. And there was a homework assignment that I was going to assign as the last one, but we're not going to have time to do it. So I was just going to talk through it together today. I think it's a good exercise to illustrate some of the concepts that we're seeing right now in the classification context. These are the classification slides, and we saw this slide last time. Remember, classification, we're thinking about assigning individuals to one of some predefined classes, cancer versus healthy, tumor class A, B, or C, or D, or whatever. And there's an optimal kind of guiding standard that we can write down. There's lots of different ways to do this classification. You could have really flexible, complicated methods like support vector machines. You could have simple methods like naive Bayes, linear discriminant analysis and stuff. But for a given setup, if there is a probability distribution that applies to the data we're seeing, then there is an optimal classifier. So the best you can do, if your input variables have some distribution, whatever that distribution is, doesn't have to be normal, whatever the distribution is, call it the probability of your data. And it's allowed to be different by class. One simple way to do this would be, I'm going to say my input variable is normally distributed with mean mu1 if it came from class 1. And normal with mean mu2 if it came from class 2, and so on. That would be one simple way to assign a probability distribution, also called a likelihood in the notes here. And if we have a prior distribution, if as you randomly draw individuals from the population of interest, what is the overall proportion of times that you see these different classes? What is the overall probability across the whole population of having cancer, say? And this is something that we can figure out numerically later. The main pieces that we would require are these two here. If there is a likelihood model for our input variables by class, and if there's a prior probability for the classes, the best classifier possible in terms of minimizing the misclassification error rate is called the Bayes classifier. And Bayes classifier is just an application of this Bayes theorem or Bayes rule. The probability of that an individual goes to class K, cancer, given their input variables, so show me your biomarkers, and now my probability, my posterior probability that you are cancer equals Bayes rule. Likelihood times prior divided by normalizing constant. Likelihood times prior is the main thing we need. And what the classification would be is here's the biomarkers, maybe a vector of biomarkers for an individual. We can go with this formula, estimate the probability that you are cancer, given your biomarkers, is such and such. And the probability that you are not cancer is so and so. My classification would then be based on those two estimated probabilities. I might, for example, say if the estimated probability you have cancer is bigger than 0.5, I'm going to predict you have cancer. But maybe there's a better place to say you have cancer than 0.5. Like maybe I need to be more careful, only if the probability is estimated to be bigger than 0.9 or something. But the big idea in classification can be formulated this way. Think in terms of a model for your input variables by class, a prior probability for the classes. Then what you would like to do every single time is the Bayes classifier, because this is going to make the fewest mistakes possible. The problem, of course, is that we don't know the likelihood. We can assume that maybe it's normal or something else. We can try to investigate what is plausible for it. We don't necessarily know the prior probabilities either in practice. So Bayes' classifier is the ideal, but it's not always practicable. Right. Let's meet one way to employ Bayes' rule. It's called linear discriminant analysis. So you've heard of linear discriminant analysis, LDA. It's a very popular classical technique for classification. It's basically an application of Bayes' rule in the context of normally distributed input variables. That's like the natural place to start. Normal distribution for my continuous input variables. Right. So let me skip forward a little bit. Well, I'll just say a couple of words here and then we'll skip forward, I think. Normal distribution is shown at the top. That is the density. That's the formula for the density. If you were to evaluate that function up at the top for a bunch of x values from really, really small negative to really, really big negative to really, really big positive and draw a histogram, it would look like the normal curve, bell-shaped curve. If you were to evaluate the function and plot the resulting evaluations, it would look like the bell-shaped curve. Mu k is the mean, and sigma squared k is the variance in class K. We might have 3 classes, tumor class A, B, or C. This model, this likelihood model, says that the distribution of our input variable in class K is normal with mean mu k and a variance, sigma squared k. So all we're saying is that, draw a picture. In a univariate case, we have one input variable that's numeric. And suppose we have 3 classes, tumor class A, B, or C. What we're saying is that there's some distribution of biomarker PSA measurement maybe for prostate tumor type A. And there's another distribution for prostate tumor type B, and maybe there's another distribution for prostate tumor type C. There's 3 normal distributions. They're distinguished by their means and by their standard deviations. But then the shape of the distribution is normal. So that essentially shows us how we can come use Bayes' theorem, because this piece up at the top, this likelihood, is now, we're saying, a normal distribution. So with a normal distribution, if we have some prior probabilities pi k, among all people with prostate cancer, we know maybe that 40% are class A, 30% are class B, and 30% are class C, maybe, across the whole population. So I'm going to use as my prior probabilities. Before I look at your biomarkers, my best guess is what it is in the population, my priors. So the posterior probability, the Bayes-based probability that an individual has tumor class A, say, given their PSA measurement, is plug and chug. This is just plug in the normal density, and a computer can do it for you. So you would evaluate this for P for A, P for B, P for C, and you'd have to pick. How do you pick among those 3 which to actually classify to? One possibility would be just pick the biggest one. I estimate the probability to be class A because that was the biggest of the P sub Ks. All right, so this is a little bit different, but it is useful. the idea of a discriminant function. Classification is specifically the prediction aspect, where you're trying to say, I predict you have cancer. There's a related bit of insight that we can pull out of this exercise that is a little bit different. It's called it's a discriminant score. It is a way to boil the data down to a smaller dimension in a way that highlights differences between the classes. When we did principal components, we were interested in boiling our data down to a simpler representation that was informative about the structure, interrelated structure of the variables. This is a lot like that. We're going to take our input variables, which may be multidimensional, and boil them down to an informative, simplistic representation, a discriminant score, not a principal component score, a discriminant score. And if we make, say, scatter plots of discriminant scores, like we learned things by looking at scatter plots of principal components, if we make scatter plots of discriminant scores, we'll be able to see what makes the groups different. We can learn some things about what makes the group different. Classification is just, let's just predict. Discriminant scores and exploring the discriminant scores can be informative about understanding what's different. Okay, so where does this thing on the screen come from? Delta K is basically, let me come down and show you the generalized version of it. Okay. Delta K is a distance, let's see, X transpose K. Delta K is, it's based on the distance between the input variable, or in this case variables, and the estimated center of each of the class-specific distributions. What does that mean? Back in the picture, suppose we have, this is our model, that there's 3 classes. Each of the classes has its own mean and its own variance. What we're going to do as a simplification measure for now is restrict that everybody have the same variance, which may or may not be reasonable depending on the setting. When we say linear discriminant analysis, we are making an assumption that the variances are the same. There's a way to get around that. That's what's called quadratic discriminant analysis. Quadratic discriminant analysis, we'll see, allows for there to be differing variances, but it's more, yeah, we'll talk about it. So suppose that my model is there's 3 normal distributions, there's 3 means, there's 1 standard deviation. If I wanted to estimate these distributions, if I had a sample from the class 1 population and a sample from the class 2 population and a sample from the class 3 population, I could estimate all these things. That's what the training data are for. Training data, let's go get all the class A individuals and let's estimate a mean and for them, and we'll estimate a standard deviation that's kind of pooled between all the classes, because we're going to, for simplicity, assume that it's the same. It is a mixture model, yeah. It's like saying when you draw from the population of people with prostate cancer, you're either going to get one of these 3 classes. And depending on which class it is, it comes from one of these 3 distributions. So it's a mixture model. If you were to say like the overall distribution of PSA, you could write it like some constant Q, like a proportion of times that it comes from the first class plus a proportion times that comes from the second class, and so on. You can write it like a mixture. Yeah. So if you can estimate those things from your training data, then when a new observation comes in, PSA is, let's say, that X that we observed for somebody. Then there's multiple ways to think about it, but basically we'd like to ask which of those three distributions is that X most likely to have come from. One way to ask would be who's got the highest density. This mu1, it's basically at 0. So the question is really between class 3 and class 2. Class 3 has higher density at that location, so we would classify to that. Turns out that's equivalent to asking what's the distance between x0 and the middle, the mean, the location for class 3. And what's the distance, so we could compute this distance. And then what's the distance to that one, and what's the distance to that one, and assign to the class to which it's nearest in a vector sense. In this case, not vector sense, this is univariate. But it's easy, I hope, to translate to, instead of just PSA, suppose we have 15,000 gene expression measurements. Then it's not a univariate normal setting, it's a multivariate normal setting. So suppose we had PSA and age or something. PSA and age are the two input variables. Then it becomes a surface. It's a normal-like surface. Go to 15,000, and you can't make the picture anymore, but theoretically it's this elliptical thing that's in 15,000 dimensions. But in theory, that univariate normal stuff translates to a vector representation. So this is the multivariate normal distribution, and we can do this linear discriminant analysis stuff by just taking some vector operations on this. There is a corresponding discriminant function, and this discriminant function is, I can't remember if it is equal to the distance or if it's some transformation of the distance. It's a function of that distance that we were just talking about. What's a sensible way to classify individual who came in with PSA x0? One sensible way to motivate things would be to ask, who's that one closest to? Is it closest to mu hat 1, mu hat 2, mu hat 3? If x0 is no longer just PSA, but it's 15,000 gene expression measurements, I could do the same thing, it's just a vector operation now. I have a vector of 15,000 things. Who's it closest to? The vector of averages for class 1, 2, or 3. And if you write out that vector distance, you'll see this. So this comes from the application of the density. But here's the input. So these would be the 15,000 gene expression measurements. This is a covariance matrix for this multivariate normal. Univariate normal, there's a variance. If I have two variables, each of them has a variance, but they also now have a covariance. It's a scaled version of the correlation. As soon as you have multivariate data, you have this co-relationship possibility. So instead of just tell me two variances, one for each of the two variables, we need the two variances and their covariance. So that capital sigma is a 2 by 2 matrix. The variances are in the diagonal, and the covariance, which is symmetric about the diagonal, is in the off diagonal. Capital sigma, let me just write this out. The univariate normal distribution, the density function, is equal to 1 over the square root of 2 pi sigma, that's the standard deviation of the distribution, e to the minus 1 over 2 sigma squared, x minus the mean quantity squared. That function, f, is that. It's centered at the mean, and the distance from the middle point to the point of inflection out here is the standard deviation. sigma. That's a univariate normal distribution. Now let's think multivariate, like 15,000 gene expression measures. There's a corresponding distribution. X is now a vector, so that underline means vector. And this is I got to look it up. 2 pi to the minus p over 2, I think, determinant of sigma, or 1 over the determinant of sigma, e to the minus 1 over 2, x minus mu transpose, sigma inverse x minus mu. Not expecting you to be able to reproduce that on the exam or anything. I'm just saying there is a multivariate version of the normal distribution. In 2 dimensions, it turns that bell-shaped curve into like a bell-shaped surface, 2-dimensional. 3 dimensions, you can't see it anymore. But it still translates. There is still a multivariate normal distribution. 15,000 gene expression measurements, we could say maybe they're multivariate normal. That means every one of them has its own mean. So here's 15,000 means, and here's a 15,000 by 15,000 covariance matrix. Good luck. Okay, so the LDA model would say there's one of these for each of the classes. There's a mean for class K, a mean for class K. And every time we see an input vector, we want to basically evaluate this for each of the classes and pick the one that's got the biggest density. That's equivalent to ask which of the means, which of these mu hat k's is x closest to. So we could compute a distance. Turns out we don't use a Euclidean distance because of the issue of differences in scale, possibly. So there's a statistical distance that's used. Statistical distance, which is x minus mu k transpose sigma inverse x minus mu k hat. And you could square root that. That's a distance. It is the Euclidean distance, except that capital sigma inverse in the middle is weighting things to allow for differences in scale and also to accommodate correlation. It's a pretty, I mean, it's interesting. I claim it's interesting. So in comes a new 15,000 vector of gene expression numbers. We can compute this distance to class 1, compute it to class 2, compute it to class 3. If you compute that thing through, like x transpose sigma inverse x, work that through, you'll be looking at that. This is called the discriminant function. If you compute this for class 1, 2, and 3, then you know how to classify. Who's it closest to? I'll show you something, just self-promotion. Probably my best paper. Is all about that stuff. It's a classification algorithm for omics data, and it's basically linear discriminant analysis with some bells and whistles. So here's multivariate normal stuff. Here's Bayes' rule, and so on. So have a look if you're interested. Classification analysis, or classification of microarrays near centroids, 2005. Okay. So in 2 dimensions, suppose we had 3 classes. We're going to take your PSA and your age, x1 and x2. And suppose that in reality, in terms of x1 and x2, the left panel of this picture shows you where the different classes live. Like the distribution of x1, x2 variables for the blue class lives right there. That might be like a inner 95% contour of a multivariate normal. So most of the distribution is right there. Most of class 2 is there. Most of class 3 is there. If you apply LDA, you're going to assume multivariate normality. So you're assuming there's these elliptical mounds, 3 of them. You have some prior probabilities. In this case, let's say every class is equally likely. That's one valid prior choice. Yes?
Can you do this? So you have to have a distribution set up of already known data before you do this.
First of all, you have to have training data, which is data for which you know the answer. Cancer, yes or no. That's data you can learn from. Okay. You know which category. The training data means you know the category. So you have like maybe manually determined the category for each of these observations. And you're gonna use that so that when a new set of markers comes in for which you don't know the category, you predict it. You compare it over here to the training data and might say, oh, this is most similar. This set of markers is closest to what I saw from the training data for this group. It looks most like this group. So I'm going to classify, I'm going to predict that this, even though I don't know the answer, I'm going to predict that it's this one. Classification is supervised learning. So you have to supervise the algorithm by saying, these are the groups. If it's cluster discovery that you're interested in, there are other techniques that are related. Cluster analysis, is the exploratory choice. But I would say, yeah, to answer your question, classification, discriminant analysis is you have the known quantities for some training data. Okay, left panel is kind of like looking straight down on these multivariate normal distributions. You can see there's some overlap between them. This particular simulated case, P is equal to 2 dimensions, K is equal to 3 classes, and there's not perfect distinction between the 3 classes. For example, right in the middle, those are PSA and I'm making these, it's not PSA and age, but let's say it's PSA and age values that are pretty consistent with all 3 classes. In particular, these 3 regions aren't completely exclusive of each other. So it's not going to be an easy job to classify everybody. The Bayes decision, okay, so the Bayes rule is the best classifier. It is LDA if the LDA model holds. The LDA model is multivariate normal and equal covariances between the classes. But if that holds, best you can do is Bayes rule, and the solid lines mark out what the Bayes rule is. The best you can do on these data in terms of minimizing errors is illustrated by these lines. If you're in the region that's been kind of shaded orange, if your PSA and age is in there, then you are classified to that group. If you're in this region, you're classified to that group. And if you're in that region, you're classified to that group. That's the Bayes classifier in this case. And it's not perfect. So there's an orange diamond, for example, that is in the blue region. That orange diamond would have been classified as blue, misclassified. It shouldn't be blue, but the best we could do, according to our model, is the Bayes one. Let me talk about this picture for just a second. We did principal components as a way to explore multivariate data. 15,000 gene expression measures. We could explore structure among the individuals. What we would, that's a neat task to take multivariate stuff and boil it down to a 2D picture. In the context of discriminant analysis or classification, we're interested in seeing how the classes differ. So what is a useful picture is to plot the discriminant values against each other. So k minus 1, yeah. We would have, in a three-dimensional case, we would have a discriminant value for all three of the classes. What's the distance to class 1? What's the distance to class 2? We would have a third one as well. We could plot those in a three-dimensional picture. This one is just showing the first two. But it is, think of it like a PCA plot, scatter plot of the first principal components. But now the apparent groupings can be interpreted as grouping together individuals that classified similarly. So I'll just say, bear in mind that a discriminant plot can sometimes be informative. Don't need that. Okay. This is good. I want to talk about this. Here's some example data, not bioinformatics data, but the issues here are relevant. Suppose we're doing classification. Instead of credit default, let's say cancer versus normal. So instead of true default status, we're going to say true cancer status. Instead of predicted default status, we're going to say predicted cancer status. Out of okay, and this table shows in our training data, for which we had, let's say, 10,000 individuals. For each of our 10,000 individuals, we knew cancer status. Training data, we know the classes. If we were then to apply the model back to the training data, how did it fit the truth? Is the question. Here are predicted values from applying our model, and here are truth. How well did we do? So we can see, for example, that out of here in this column here, where it's labeled no, out of the 9,667 people who did not have cancer, we correctly classified 9,644, which means we misclassified. We told 23 people who didn't have cancer that they have cancer. So we made mistakes on those 23 people. Over here, among the people who truly had cancer, we correctly classified 81 of them as having cancer. But for 252 of them, they had cancer, we said no. Those are also errors. These are kind of distinct, though. In the first case, these were false positives. I said yes, but in reality it was no. These 252 are false negatives. I said no, but the truth was yes. You would prefer not to make either type. Sometimes it's easier to make one than the other. Okay. The overall misclassification rate for this pretend example was 2.75% because they made 23 plus 252 errors out of 10,000 predictions. That's a pretty low error rate. So that sounds pretty good. But just thought experiment, suppose we, in this particular case, said no, you do not have cancer to every single person, regardless of their input variables. My accuracy, or my error rate, would just be 333 divided by 10,000. It'd be pretty low. A little bit bigger than this, but still pretty low. So this misclassification rate is an overall assessment. How many total errors did you make? But it can hide some subtleties because, for example, the false negatives, we made a false negative most of the time. 2.75% misclassification rate, that's good. But there were 252 people who had cancer that we didn't catch. So like the rate of false negatives, 252 out of 333, that may be unacceptable. So here's lingo that goes with what I was saying. The false positive rate, that's the proportion of true negatives that you classified as positive. In this case, we did a great job. We were hesitant to call people cancer, so we tended never to call people cancer. The false negative rate, those are folks who the truth was yes, we said no. And here it was 76%. Looking at that 2.75% on the previous slide only would completely hide this. And this huge false negative rate, like I said, may be unacceptable. So I say that not to doom the procedure or anything, just to kind of motivate what we'll do eventually, which is to try to better balance both of these. I would prefer not to make much of either type. Okay. When we do linear discriminant analysis, we're going to get those posterior estimates, those estimated probability that you are cancer given your PSA, and probability that you are not cancer given your PSA. What should you do with those estimated probabilities? Suppose the probability that I'm cancer is 0.51. That's bigger than 0.5, so should I tell the patient that I think they have cancer or not? Or should I be like more strict? Maybe the instrument really would be better if it was more strict. I'm only going to claim cancer if the estimated probability is greater than 0.95 or something, if it's really convincing. We don't know right now, without some help from the data, what the right choice is in terms of best balance between these errors, false positives and false negatives. This picture illustrates the idea. We could change the threshold. Should the probability, should the threshold be 0.5? If P is bigger than 0.5 for cancer, I'm going to classify you as cancer. Or should it maybe be something smaller? And in this case, here's the error rate, the overall error rate by false positive and false negative. Let's see, the overall error rate is the black one. The false positive is the orange one, and the false negative is the blue one. So for example, if we took what would be the most natural choice as the default, which is 0.5, cancer or healthy, well, which of the estimated distributions is most likely? Is the estimated probability of cancer 0.51 or not? Could do that. That corresponded to a pretty low overall error. That was the 2.75% that we saw. And a low false positive rate. We did fine with the false positives, but the false negatives were enormous. They were way up here. So you can explore, what if we lowered this? This is converse to raising it, I think. Basically, we're changing how extreme the probability has to be. It doesn't have to just be assigned to the group that's most likely. How much more likely does it need to be? And it turns out that, like right here, there is, or let's do right here. Right here, if the estimated probability is 0.1, I still have a pretty low overall error rate, and the false negative rate has been dropped by like 50%, or by 50 percentage points. So it's a lot smaller. All that to say, often in the classification or prediction context, we have some method that we want to use, whether it's linear discriminant analysis or support vector machines or whatever. Every one of them is going to have some kind of decision that we have to make before it can actually be put into action. Apply LDA just means estimate the means and estimate the covariances, and then it will give you back probabilities. The probability of cancer is this, probability of not cancer is that, given their inputs. We have to make a decision about, do I draw the line at 0.5, or do I need to be more strict, or whatever. Every method will have something like that you have to tune. You have to tune the model to work best for your particular data. So you will want to make pictures like this and pick the threshold in this case, or more generally, whatever the tuning parameter is for the method of choice. You'll want to pick it so that it strikes a good balance, a tolerable balance between all of the error rates, not just misclassification rate. One way to make a picture like this is with cross-validation that we'll talk about soon. It's a resampling technique that allows us to get reliable estimates of error rates by resampling from the one sample of data that we have. An ROC curve is good to know. It is a way to visualize, another way to visualize the trade-offs between the two different error rates. So an ROC curve, a receiver operating characteristic curve, puts the false positive rate on the horizontal axis and the true positive rate on the vertical axis. And what you would like is to have high true positive rate, low false positive rate. So ideally, you would have a classifier that sits on this curve somewhere up in here. The ROC curve would tell you, suppose you're going to do linear discriminant analysis and you want to know what should my threshold be for classifying, for assigning to the different classes once I have those estimated probabilities. You could vary the choices of the threshold over a wide range of values, and for each one of them, use cross-validation to estimate the false positive rate and the true positive rate. Then you could make this picture for your data. So your one set of training data, you could use it and say, let's do LDA, make an ROC curve, and pick, based on the ROC curve, looks like the best I can do is right around in there. That kind of reaches as close to the upper left corner as I can get. And then I could look back at my data, or the code that I did, and figure out what threshold corresponds to that. Maybe instead of 0.5, this is 0.12 or something. That's the number I'm going to use as my threshold. You might sometimes see people say area under the curve. Do you have a question?
Yeah, I think I might be thinking about this wrong. So what if, like if you think about your false positive rate and your true positive rate, wouldn't they have to equal up to 1? Because say 80% of your positives are true positives, at least other 20% is false positives. So why, when you're looking at the curve, are we not seeing it?
So these are more like conditional rates or proportions. A true positive rate is the proportion of the true positives that were correctly assigned as positives. False positive rate is the proportion of the true no's who we misclassified. So it's like a proportion of the males and a proportion of the females. Those two proportions don't have to add up to 1.
So yeah, I was thinking that wrong.
All right. Okay. Okay, so this is a good slide. In your homework, you're going to do linear discriminant analysis. You're going to do what's called quadratic discriminant analysis. You're going to do what's called naive Bayes. What are those things? They are all the same thing as what we just did, just different tweaks on them. They're all efforts to reproduce Bayes' rule. That's the best we can do if we know the distributions and we have prior probabilities. Best we can do is this. So LDA, QDA, naive Bayes, they all say, let's say normal distribution. Surely that's not true with my 15,000 gene expression measures. Maybe more so after I log transform them or something, but almost certainly not multivariate normal. All models are false, but some are useful. It's a famous statistician phrase. I forgot who said it. And another thing about normality is that it gives us some nice analytical results that makes it easy to implement and has some nice distributional results that helps us have like p-values and confidence intervals, inferential stuff. So the LDA model said multivariate normal, each class has its own mean, but everybody has the same covariance matrix. That's a strong assumption. The variances of my 15,000 gene expression variables are the same whether you have cancer or not. If you have cancer, I think it's pretty clear from the research that there can be big differences in, there can be an explosion in variability, when cancer hits. Things go out of whack or something, and there's more variability. So you might be concerned about that assumption. If you allow for each of the classes to have their own set of variances and covariances, their own covariance matrix, call it sigma k, then you get slightly different results, but it's still multivariate normal and Bayes' rule, and it's now called quadratic discriminant analysis. Linear versus quadratic has to do with the form of the quadratic function, of the discriminant function that we wrote down. Linear discriminant because there's a common covariance. That capital sigma drops out of the expression, and the expression is linear in x. In quadratic, you can't do that simplification, and the discriminant function is quadratic in x. Roughly speaking, quadratic discriminant analysis is a more flexible method than linear discriminant analysis because it allows for there to be more nuance in the distinctions between the classes. With greater flexibility, we talked in a previous lecture, with greater flexibility can come overfitting, can come greater variation. So remember the goal of reducing bias and variability of the results. More flexible is nice, but it will often come with a penalty in the form of more variability. Naive Bayes is another take on the LDA model. Instead of a covariance, it assumes that all the features are independent. If all the features are independent, there are no covariances. Covariances are just scaled versions of correlations. So if I'm independent, if x and y are independent, they're not correlated. In which case capital sigma is a diagonal matrix. Zeros everywhere but the diagonals. Things simplify greatly. There's no longer these enormous 15,000 by 15,000 covariance matrices that have to be estimated. It's called naive Bayes in the sense that surely your input variables are not independent. The only reason we would pick this is for computational simplicity, and small sample size cases where we don't have a choice. All right. So I hope, let that simmer, and hopefully we now understand classification, the role of Bayes' rule in classification as the ideal that we would like to implement every time if possible, LDA, QDA, and naive Bayes, all as the same basic idea of let's assume multivariate normality, let's cook up some prior probabilities, and then apply Bayes' rule. There's lots of different options. I think I'm going to quit on this set of slides. Yeah, that's it for this set of slides. Next up, we'll learn some other techniques. I do want to show you some of the options, like the tree-based methods are interesting, and they're pretty powerful. Support vector machines are very powerful. Right, so that's what we'll work on next. Questions? Yes?
So we will have demonstrations on how practice this classification in the later lectures.
Yes. You have all of next week. So the homework's not due until the week after. And next week we'll do more R. So I'll show you. In the meantime, you can look at the con script. So there was the con data, and there's a conscript.r. I haven't downloaded it here yet, but it's on eCampus, conscript, and it's got examples of LDA, naive Bayes, QDA, random forest. So you could adopt the code in there very easily. It's not hard to use the code. All right. Have a good weekend.